Well, thank you very much for coming in person and online. It's a really great pleasure for me to introduce the speaker today. So we've got Dr. Tickle here, University of Bristol, where he's a research fellow, and his research interests are in time series and multivariate inference. His PhD was at Lancaster, and it was on change point detection. And he's applied his ideas to a whole range of things, including stock market, telecommunications, and terrorism incidents, which is the topic of talk. And we're particularly very lucky to have him today because he's just in a transition moment, and he'll be joining industry at the end of the month. So thank you very much, Sam.
Thank you, my pleasure. And as Mia says, I like to keep things as cheerful as possible. So I'm going to be talking about terrorism today. So thanks are due to many groups. So obviously I'm affiliated currently, as of the next week, to the University of Bristol, where I'm a research fellow at the Harbour Institute. And some of this work was thought about while I was still a PhD student at Lancaster University. So some of this dates back as far as that. And obviously, as ever, EPSA on high. Many thanks are owed. So I'm going to try and discover how to transition from slide to slide. I assume I do that with the arrow keys here like this, or just by clicking the screen. Great, cool, excellent. I swear I have minimal technical competency at the very least. Great, so the key word in this title, for now at least, is changes. And indeed, this is a, thank you very much, Sean, cheers, thank you. So useful, I can get the simplest things wrong. Sometimes even the not so simple things wrong, as we'll be discovering shortly. So the key word in this title is indeed the word changes. This is a change point detection talk, but with a flavour of thinking about terrorism as well. So just as a very, hopefully, either very quick refresher or at the very least, something which is patently clear. What is a change point? Just a point in time in which, surprise, surprise, something changes, some aspect of a data generating process. This can be a mean, it can be a variance, it can be a mean and a variance, it can be something like a rate. It can be even something just, changing from one distribution to another. And it's been an area of interest in statistics and elsewhere since the 1950s at the very least. So I would say the first paper on this was sort of 1954. That sort of first was the genesis of things in this sense. But things really got going with the turn of the millennium. And in the 2010s, we saw an explosion of techniques and interest in the setting where you have a single stream of data, single sequence of data, not necessarily a stream. And what we want to do is you just want to detect change points after we've seen the entirety of the data, so the offline setting. And there are some enormously successful techniques there now. We've got PELT, Proven Exact Linear Time, which is thousands and thousands of citations, 2012 paper. But there are a few problems that remain. So the problems that remain essentially are what happens when the problem gets quite complicated? What happens when your data, well, we live in the big data era now, I'm told the ChatGPT era, I think, we've moved on from big data now, ChatGPT. Particularly when we have this sequential setting where we're detecting, or want to detect changes in real time. So we want to detect changes almost as soon as they happen. Think, for example, I guess I'm here in the BSU. I should be talking about medical examples as much as possible. For example, if we want to have automated way of detecting when something is going wrong in heart rate monitor, a patient is undergoing cardiac arrest, you've not got somebody there to supervise it. I imagine there's already some system to do this, but you can use change point detection to ascertain, hopefully, when something is not quite right. We want to be multivariate if we can. So all the sort of toy examples that I was pointing to on the last slide, just single sequence. What happens when you have multiple things going on at once, multiple sensors? So again, just to go back to the medical example, you might have several things hooked up to the patient, and it might be the case that just one thing is going wrong or lots of things are going wrong at once. We want to be able to detect both types of behavior. And finally, again, another problem with these toy examples is that, again, I was sort of specifying change in mean, change in variance, and everything looked rather Gaussian. And in fact, everything was Gaussian because it was just simulated toy Gaussian data. What happens when we don't have a nice parametric model for things? What happens when we just have data given to us by a practitioner who says, I'd rather like to find some changes, and I have no idea what my data really can be modeled like? So I'll be talking about that with respect to Omen later on. So Omen is the kind of new method that I've been thinking about, not published yet and unlikely to be published in the foreseeable future as I'm leaving academia, but will exist as a GitHub repository with everything I'm going to talk about later on. In the meantime, I'm going to talk about the very cheery topic of terrorism, because why not? It's a Tuesday afternoon. So I saw this picture a few years ago, and I just had one of those moments where I must find out more. So this is from the National Consortium of the Study of Terrorism and Responses to Terrorism, or START. Yes, the A in the acronym stands for AND. Don't worry, with regards to terrible acronyms, you ain't seen nothing yet. So this is an intensity map of terrorist incidents worldwide from 1970 to 2015. And this map has come about through diligent, very, very diligent cataloguing of terrorist incidents by START, which is based at the University of Maryland, from 1970 to the present day. Why 2015? Well, it's because that's the most recent year in which they could be bothered to draw the map. So they've been continually refreshing the data since then. So the cataloguing has carried on. It was, I think, briefly defunded during the Trump administration, but it's now fully funded again. So it's continuing to collect data. I think. Don't quote me on that 100%. So a few things stick out to me when I look at this map. So obviously, we can tell if you're, well, I apologize incidentally if anybody's colorblind in the audience. This might not be the most friendly talk for you, but suffice to say that the greater concentration of points, the more red things are, the more incidents happened in that 46 year period. So for example, obviously, I'm British, as you can probably tell. The reason why Northern Ireland is in red, for example, is unfortunately all too plain to me. 1970 to 2015 weren't exactly sort of peaceful and tranquil years in that part of the world. And also, alas, we can tell that certain parts of the world, which we would perhaps a priori think had an intense terror activity, do indeed manifest that. However, this is just one snapshot of 46 years. And I was interested to attempt to ascertain whether the probability of a terrorist attack changed markedly in these places and indeed everywhere else over time. So I was interested in the temporal picture rather than just simply the spatial picture. So just to summarize some of what I've just said, I've got to state that this is copyrighted to the University of Maryland or I get into terrible trouble. Got every single incident. I'll define what an incident is in a moment, incidentally. I should have been more careful to say that it's sort of clearly a fluid definition. One thing I've got to point to is that 1993 is not in the database. And the story behind it is probably worth a 30-second diversion. So back in 2001, an unfortunately rather notorious terrorist incident necessitated thinking among certain people in the United States that said, oh, we've got this resource which has terrorist incidents from 1970 to the present day. It might be rather good to understand that. And prior to 2001, all this was on paper, sort of a box for each year. And in the move to digitize it after 9/11, 1993 just got lost and they've never found it. I think they have gone back since, backdated it and just added it in. And for bizarre reasons that escape me, that's not available in the publicly available copy of the database. So there's a sort of one you can pay for, but I never bothered with it. So in all the analysis to follow, the 1st of January 1994 follows on from the 31st of December 1992. So that's something to be borne in mind. Okay, I think I've touched on everything else. So I will address the elephant in the room. Obviously, what defines a terrorist incident is going to differ between any two people, but this is the definition that the consortium that START went with. So in addition to there being violence involved, which I think makes sense, has to be violence committed by a non-state actor. Two of the following three criteria must be satisfied by the event. So first of all, there must be some wider goal. By wider goal, political, economic, religious, social. And the one that I think makes perhaps the most sense is that the intention of the event must be to affect more than those that are immediately impacted by it, larger audience than the immediate victims. And finally, there's a slightly bizarre criterion at the bottom here, which is that the action must be outside the parameters permitted by international humanitarian law. Now, notice that this says two of the following three. So technically, this means that there are terrorist incidents which are allowed by international humanitarian law. And this took a long time for me to square the circle of this. It's basically to sort of distinguish between different types of war crime. At this point, things got a bit depressing, and I thought, well, I won't carry on. I'll just take this as read. I'm a statistician. I'm not somebody who wants to sort of be thinking about war crimes and terrorism all day, at least not directly. Cool. But one thing we can get out of this is a pretty picture. So the first pretty picture is this, and again, my second apology to any colorblind folks in the audience. This is the regional stratification of the global terrorism database. So we have here 12 regions into which stratifies the world. North America, Central America, South America, Sub-Saharan Africa, and so on. And at first I thought, okay, fair, it's just 12 different parts of Earth, who cares? But what I then thought was, actually, this is quite a nice get out of jail free card for somebody who wants to turn this into a temporal data set. What I wanted to do was to somehow aggregate events, maybe count them by month in certain regions of the Earth. I was thinking by country, but certain countries like Australia and New Zealand barely ever get terrorist activity. And to give a slightly more humorous example, in the entire 50-year period of the global terrorism database, North Korea has had exactly one recorded terrorist incident. I would bet my life that there have in fact been more, but it's, as again, the communication to North Korea isn't great for reasons that I won't get into now. So 12 regions, and we can, let's say, do a count per month across each of the 12 regions. So we can aggregate all of South America, say, into one time series and look at the number of incidents per month from 1970 to essentially the present day. So pick your favorite region or the region you want to sort of focus on. What I'm going to do on the next slide is have a picture of all of these regions, but with the count per month, with the colors identical to the pictures that we can see here. So North America will have purple for its series and so on. So here it is. And the region that I'm saying is the most interesting, or the one that I picked as my favorite, is the Middle East and North Africa, the one in black, which is, for anybody who's can't quite tell, this is the one that becomes dramatically worse than the rest in the 2010s. And we can probably all work out why. So the Arab winter, as it was called, following the Arab Spring in late 2011, sort of precipitating the various civil wars that we saw at the time, and some of which are still going on, unfortunately. But there are certain things that we can eyeball here and say, yeah, that seems to be a change point in the vein of that first slide with the toy data. So again, the aforementioned Middle East and North Africa phenomenon from 2011-12, where there's a sudden explosion in terrorist activity. And if we look back at Northern Ireland, or Western Europe, I should say, the series in silver, if you look here at the 70s, gesturing with the hand, if anybody in the room can't quite see, but I'll also try and do it with the laser pointer. Right over here towards the left in silver, we see Western Europe. That appears to be exclusively Northern Ireland activity. And there are some interesting features in there that I'll point to in just a moment. So we can see some changes, but what I really want to be able to do is attempt to have good statistical power in two settings. One, I want to be able to sort of have something which automatically says, yes, there's something going on in one region because the economy is blown up in the Middle East or something. Or conversely, there's something that's happened that's affected the probability of a terrorist attack everywhere. Don't know what it is, but it seems to have affected everything. So we want to be able to have good power to detect both of those two types of change. And we could refer to these as local and global. I'm going to call them sparse and dense, just because when I'm thinking about this, I'm thinking about this in terms of a theoretical data set, and I'm saying it's sparse in the variance or dense in the variance. So if I fail to highlight that point again later, proverbially slap me on the wrist. So sparse and dense. Here it is again, just overlaid with the map. So if you were interested in a specific region, here we are again. But yes, we can clearly see that change point detection is going to be of interest to this data set just by looking at the data. Okay, so I mentioned Northern Ireland before and said we'd come back to it. You might be wondering, well, has change point detection, the global terrorism database, just come out of the blue as an area of interest to just sort of think about at the center of this Venn diagram? There are people who have thought about it. So in particular, Lefree, who is one of the researchers on the global terrorism database, primary researchers, used the database to perform analysis on certain events or policies enacted by the British government between the late 60s and the early 90s in terms of whether it actually had an impact on the level of terror activity overall in Northern Ireland. And the answer was that there was almost always more of a backlash than a deterrence effect. The only one that seemed to have a deterrence effect, according to them, was Operation Motorman. The stats they did was relatively straightforward, not quite getting into the stuff that we're talking about later on, but still, I think, interesting and worthy of further investigation, if only I had done it. Another really rather fantastic analysis comes from Raghavan et al. 2013, using a hidden Markov model to focus on Colombia this time, between 1998 and 2006. This was a by-day time series distillation, so we've done by month, but nothing to say you couldn't do it by day. Be a lot sparser, I suppose, thankfully. And they found a significant change at the end of June 1998. And this is interesting because it was at this precise moment that the United States put a lot of money into combating the drug economy in Colombia, and it seemed to work. So the slightly sort of unpleasant coda to this is that in 2000, I think the money was sort of relaxed a bit. It's like, oh, well done, chaps, we've done it. We can defund it now. And then suddenly terrorism shot back up. And I think it was only in 2016 that there was peace made between FARC and the government. I think it was 2016. So what I'm saying is that this has been done before and it seems to have worked. Okay, so what I want to do now is talk about some published work, namely a method called subset, which tackles the multivariate part of this problem. So I'm not going to touch on the online stuff yet, and I'm not going to touch on the non-parametric stuff yet. That'll come in section 3, providing I don't waffle on too much, but I will touch on the multivariate stuff. And I mentioned before about sparse and dense change points. And just to really bang on about this, in the multivariate setting, the question, what is a change point, becomes a bit ambiguous. Here is the basic picture which explains why. On the left, we can see a change from the red region to the green region. Apologies to any colorblind people in the audience. I'm a terrible person, I apologize. From going from red to green, we have a sparse change point. Sparse change point, again, just being something which is sparse in the variates, only affects a small subset of the variates. Yes, I did just describe a small subset as being 25% of the variates in the system. And on the right, we can see a change from green to yellow. This is a dense change point because it's affecting everything, even if it's sort of more subtle, he says, than the thing from red to green. And we want to have good statistical power in both settings. In the sparse setting, we want to be able to say, these specific variates are changing. In the dense setting, the requirement, by contrast, is if everything's changing by a little bit, so let's say there's a subtle deterioration in a patient, for example, or the terrorist attack probability has changed just slightly because inflation's gone up by 5% or something. We want to be able to pick up something that's very slight, but is happening everywhere or almost everywhere. And it doesn't really matter in the dense setting if we're not quite accurate with exactly where things are changing. It's basically just saying, yeah, there's kind of a systems failure everywhere, something subtle perhaps. Somebody needs to go in and investigate a root cause. That's essentially what's going on. So just to bang on this point one more time, sparse change on the left, dense change on the right. In the sparse setting, we want to be able to say exactly what is changing. In the dense setting, we want to be able to say, yes, something's changing, even if it's very subtle, but it's affecting nearly everything. And the very, very simplest change point detection tool is the Q-sum statistic or transform. And in a moment, I'll talk about how we adapt this to the multivariate setting. But for now, this is the original. So I talked about the original paper back in 1954. This was introduced then, or this was talked about in change point detection context then. And essentially, if we've got some, let's say, change in mean, why not? I'm feeling happy today. Change in mean problem, such as the one that we can see on the left plot here. What we can do is, if we suspect a change at time t, for t between 1 and n-1, where we have n data points, we can compute what is essentially a difference in the means from before t and after t. And if this seems significant, in particular if it's above this red threshold at a time point t, then we can declare a change point. And if we were to do this for every single candidate point, we might be able to find the best point by finding the location which maximizes the Q-sum test statistic. So in this case, I did just the obvious thing. I drew some synthetic data, Gaussian change in mean, because I was feeling particularly unadventurous. Put a change point at time equals 500. It is there, I promise it's subtle, but it is there. And then I just computed the Q-sum test statistic for each of the t from 1 to 999. And we get The maximal point of this, I think, basically at 500, maybe with plus or minus a small error. And the threshold here is essentially, we could essentially think about it as analogous to a p-value. So if we were running this on, I don't know, again, some kind of medical data set. So I had an example explained to me on the way in, but I won't sort of canvass this in full detail here, just for potential confidentiality reasons. But let's say I had something monitoring, again, heart rate. And there was something which showed that it was elevated, but only slightly. Maybe wouldn't be detectable to the human eye, as if we were looking at the thing on the right, on the left in a hurry, we wouldn't necessarily see. Then, if the Q-sum test statistic was above this threshold, then under the basic premises of the hypothesis test, we would declare a change point. That's what the Q-sum test transform is doing. But so far, so single sequence. What about when we have a multivariate sequence? Well, what we can do is we can do the very simple thing of just adding in an I. So if I switch back to the previous slide and just compare the two test statistics, all I've done is just added in an additional subindex there, I for I1 to D, where D is the number of variates. And what I'm saying is just focus on a single variate, do the same thing, compute the difference in the means, do the weighting. And then what we need to do is we need to aggregate these test statistics in some clever way that we can ascertain a multivariate change point, whether this is a sparse multivariate change point or a dense multivariate change point. And 4 methods of aggregating the Q-sum transform are as follows. So there is what we might loosely term the mean, which is just compute all of these, take the mean, and then just look at them at each time point t. And this works very, very well if you're looking for a dense change point. Because if you've got something subtle, like we saw on the previous slide, then you do the Q-sum transform for everything. For people not in the room, I'm sort of doing a kind of step with my hands and sort of moving up and down. You'd be embarrassed. You'd suffer secondhand embarrassment if you saw me. Trust me. So we can aggregate these things, add them all up, and by taking the mean, we preserve that small change in the dense setting. But it doesn't work so well if we're looking for a sparse change, because if we take the mean of one thing that's changing by a lot, and then everything else is changing not at all, then that gets smoothed out over the mean. So the top one there, the mean transform, is only really effective in the dense setting. And it's kind of the extreme dense test statistic, if you like. And by contrast, the maximum is the extreme sparse test statistic. And it's kind of obvious why. If we were to chuck out everything, except the one that looks most prominent, then if you've got a single thing which is changing, then that's probably going to be the one, well, I hope it's the one that is most well preserved by the Q-sum transform. So that works very well when you're looking for a sparse change point. There's one sparsified binary segmentation. I tend to call this the bin weight transform. And on slides later, I call this bin weight. That's my terminology, which is kind of naughty because it's not my method. But essentially what it's doing is it's censoring everything below some threshold. So it's chucking out everything below some predetermined threshold alpha, and then says just add everything else up. And this is quite balanced. So it's sort of, you can tell it's kind of between doing the mean and doing the maximum. And it works quite well. And finally, I've got to mention inspect here. It's an in-house method. It's a Cambridge method. Wang and Samworth, a few years old now, works very well. Very nice method. I'm not going to bother putting the formula on the board because my brain would hurt. But it's very clever, very involved, and I encourage everybody to read the paper. It's very nice. Okay. So far, so Gaussian change in mean. So that test statistic we saw before, it has been applied to situations that aren't Gaussian and aren't changing mean. But it's not the situations that it's designed for. It is specifically designed for the Gaussian change in mean setting. It's just a likelihood ratio. It's just what you get if you do a likelihood ratio for the change point setting, and you assume change versus no change, single change versus no change. So what people often do is take some sort of cost function approach. And I'm just going to put this formula on the board, kind of rip off the plaster. I never like seeing the formulas I write on the board, but then there we go. What we want to do is minimize a formula that looks like this. We can just think of this as a kind of fitting function, model score. The curly C here is just a kind of model fit, within segment model fit. So we can think about this as least squares or something, or absolute error loss, that kind of thing. And the beta is a penalty value. It's just penalizing the number of changes that you put in. So for every change point that we add, we have to penalize the model. We don't want the model to be too complicated. Cool. So I'll take this off the board as fast as I can before I confuse myself. But suffice to say, a lot of methods, PELT included, that I mentioned right back at the start, minimize something that looks like this using dynamic programming. And that works very well and very computationally efficient, and it can detect multiple change points. Okay, but that is still in the single variate setting, and we want to extend things to more than one variate. And a friend of mine, Ben Pickering, a few years ago now, extended this method, the cost function approach, to multiple dimensions. So I mentioned this beta penalty value before for introducing a change point to the model. Ben's particular postulation was, well, if we were to add in a multivariate change point, yes, we should add in beta when we're including it in the model. But for every additional thing, every additional variate that we say is affected by the change, we should add on an alpha. So for this change on the left here, we have two things that are being affected by the change point. So the penalty, the total penalty for that change point is beta plus alpha, so beta plus 2 alpha. And the same thing for the change point on the right, because clearly I wasn't feeling very adventurous when I set this up, and I should have had a differing number of things changing. But I live and I learn, or well, I live and I decide to go off and do something else, as the case may be, in 1 week's time. So this looks good, but the resulting method is not very computationally efficient. It's d times n to the 2d minus 1. And given that we started off with the global terrorism database, we've got 12 regions. I don't particularly want to be waiting around for something which is order n to the 23. I'd quite like to get my dinner tonight. So I think this is going to be a non-starter, unfortunately. But the issue with this method isn't so much the idea, it's the insistence that we exactly minimize some kind of cost function that we saw on the previous slide. So in much the same way that this mean test statistic and this max test statistic before were two extremes, what if we could somehow have a compromise between the kind of test statistic approach that we talked about before and this kind of nice and elegant cost function approach, which then takes something on the order of the heat death of the universe to complete? And the answer to doing that is, well, yes, we can. We can just do some kind of cost function based test statistic. So let C be a cost function, squared error loss, absolute error loss, something like that. The saving of placing a change point at time t in variate I is then just, again, kind of a likelihood ratio type thing. The cost of doing no change, that's to say the cost function of just having a single sequence, single segment cost function from 1 to n, comparing that to the cost of putting a change at time t. Very, very much analogous to the Q-sum, but a slightly more flexible in terms of what kind of problems we can solve. Then we get to the complicated bit. So this is the final test statistic, which is in this paper that came out in late 2021. Myself, Idris Eckley and Paul Fernhoff at Lancaster released this method called subset. This is the second acronym of the day. I haven't actually written on the slides what it stands for. I feel like I shouldn't, but now I've teased it too much. It stands for Sparse and Ubiquitous Binary Segmentation in Efficient Time. I told you that START wasn't the worst acronym, and I wasn't lying. So sparse and ubiquitous because, well, I wanted something which gave me the word subset because it tells you the subset of the things that change. And before you say, well, why didn't you use the word universal to stand in for dense? The answer to that question is somebody asked me that question, but that was the day after it had just been accepted as, with corrections in the journal. And I felt like a so-and-so for not thinking of it sooner, but there we go. So sparse and ubiquitous, or sparse and dense, or sparse and universal, whatever you want to say, are the key words here. So on the left side of this test statistic, we can see these D primes going on. These D primes are sparse savings. They're kind of censored savings. And this hopefully will evoke, if you recall from a few slides ago, this SBS test statistic, this sparsified binary segmentation test statistic, which had everything censored at alpha. This alpha is playing an analogous but not identical role here. And again, we have some beta penalty for introducing a sparse change point. So beta here is a slightly different thing to K, which on the right-hand side is saying, let's just add up all of our cost function differences, these DITs, savings, and then take off a K, which is specifically a penalty for a dense change point. So we now have two different types of penalty. Penalty for just a standard sparse change point, if you like, and a penalty for a dense change point, which we're just going to say, yep, everything's changing. I'm going to be aggressive and say absolutely everything is changing in this system. Cool. Managed to pointer batteries put in the wrong way, but never mind. I've broken the laser pointer, but I should come back to that later. Spot the change point, chaps, and things going wrong. Never mind. So we've got three different parameters in here. We've got alpha, we've got beta, we've got k, and this is just begging for me to say, well, oh goodness, all is hopeless. How are we possibly going to set three parameters when we're looking at data? What we've done is we've come up with a false alarm probability result, which says if you set the parameters to be this, alpha, beta, and k to be these values that you can see on the screen, then actually you get a low number of false alarms in the Gaussian changing mean set. But it turns out that actually this is transferable to non-Gaussian changing mean settings as well. The eagle-eyed amongst you who like chi-squared distributions will notice that this k seems to ape rather curiously the quantiles of a chi-square distribution with d degrees of freedom. But I won't dwell on that for too long, because here is another result which I'm going to rapidly go past, but just in case you were sort of really wondering if we're actually able to detect change points, the answer is yes. So all I want to point you to here is this delta I. So this delta I on line 3 is just how prominent the change is, sort of the difference between mean before and mean after. And if this hideous looking thing in the middle, this sigma delta I squared monstrosity, if that's large enough, then we're going to see the change point. I'm going to go off this slide as fast as I can. This just to convince people that we did actually do some theory, rather than just sort of play around with graphs in R and sort of interesting things with terrorism data. Okay, and the simulations seem to suggest that our method, subset test statistic, which is in red here, apology number 4 for colorblind people in the audience, it does seem to be competitive with other methods that we've discussed already. So what are these pictures showing? Well, along the x-axis, we have an increasing change magnitude. So this is the Gaussian change in mean setting again. And again, for anybody who's not in the room wanting to sort of suffer my secondary embarrassment, I am slowly raising my left hand up above my right hand, indicating a sort of gradually increasing change. So change going from 0 to 1. And basically, the quicker we get to 0, the better, because as soon as we sort of detect change points, it's like, yeah, we found it, and we have a lower type 2 error. So got lots of different experiments going on for 0.001, 0.002, and so forth. And in red there, with subset, we very rapidly see that gets to about 0.1 if everything's changing. So on the top left there, everything's changing, so a dense change point. We see everything very quickly. Also of note here is that the mean test statistic in the top left sees everything very quickly as well. So I said that mean was about the best you could do. It's got sort of theoretically the most sort of I will detect only dense change points type of test statistic, and we're as good as that. So that's very promising. And to be honest, the only one that seems to do quite badly here is the max, which isn't surprising. It's the one that's sort of most geared towards being good in the sparse setting. So we've got the example in the middle there, or on the top right, I should say. So we've got 50 things changing out of 1,000. This is kind of not quite dense, not quite sparse. Everything seems to be doing broadly the same as one another, so they're all doing quite well. Although again, subset seems to be performing competitively. And finally, we have a sparse change point in which subset seems to be beaten slightly by the bin weight, the SBF method, but max also seems to be doing quite well. I should mention here, before anybody says, oh, look at inspect, it doesn't seem to be doing as well as some of the others. This was me using the inspect package and not sort of, somebody who was fully au fait with exactly how to set all the parameters in inspect properly using the package. So I feel like I should point out inspect is better than I'm saying it is here, and we did comment on this in the paper. This is me, brainless Sam, trying to use inspect rather than say taking Omen. So I don't want anybody to be given the idea that I'm being unfair to inspect in any way. And this picture here just indicates that we do in fact find the correct makeup of the changes in the sparse setting, which things are changing, in other words. I won't dwell on the picture, but again, we're just increasing the change from 0 to 1, and yes, for all situations. So going from the darker reds to the lighter reds, where we have sort of 200, 400, 800, 1600, and so on, variates in the system, 0.5% of things changing each time. We do actually identify which things are changing correctly as the change becomes more prominent. Okay, but that's all very Gaussian. And we don't want to be Gaussian. We're dealing with count data, where we're looking at the number of counts per month in this terrorist activity setting. So this suggests using, say, a Poisson, or more likely a negative binomial likelihood. The reason I didn't use Poisson was because, well, funnily enough, sometimes the mean does not equal the variance in count data scenarios. So it'd be useful to consider over-dispersion of data. Hence the reason we went with that. This has been used in the sort of modeling count data, time series, change point detection world already. So Simon Wood, who was at Bristol until 2020-ish, released a paper in early 2020 in which he talked about lockdown and negative binomial likelihoods and change point detection and all that in quite an interesting paper. Actually quite an interesting argument as well. I won't get into it, but it was not necessarily what I 100% agreed with, but it was well argued nonetheless. Regardless, the two parameters in the negative binomial setting are either the mean and the variance, if you want to parameterize it that way, or the over-dispersion, the number of failures until an experiment is stopped in the sort of classical experimentation sort of setup for negative binomial likelihood, and the success probability. And I don't like referring to this as the success probability in the terrorist setting for obvious reasons, because we're looking at the probability of a terrorist attack. And the standard nomenclature for this parameter is the success probability. But heck, there it is. I'm kind of stuck with it. And it is this parameter that we're looking for changes in. So what we did in our model was we constructed the appropriate cost function, the negative binomial likelihood cost function, supported in package you can find online. And what we're doing here is we're looking for changes in this success probability, given that we can re-estimate this over-dispersion parameter every time we detect a change. So we essentially assume here that the over-dispersion parameter doesn't change unless the success probability does. That might be seen as a weakness of this model, and I would agree. We can't sort of have over-dispersion changes in isolation, but for now, we'll leave that weakness in, but I will sort of highlight it. And here are the results. So I couldn't put all 12 of the regions on the slides as much as I wanted to and sort of baffle your eyes even further. Here are 3 regions that I picked out as being particularly noteworthy. So Middle East and North Africa again, found some change points, North America again, and Western Europe. And we can see straight away that most of these change points are sparse. Most of these change points are not shared across the series. The exceptions are the trivial change points of we go from having data to having no data at the end of the stream. This is just something that change point people like to do. And at the beginning, we go from having no data to having data. I'm sorry that we do that. It's just the way we roll. But otherwise, we can see, for example, there's the late 1970s in Northern Ireland. There was a time when I knew exactly what happened in February 1975. There was some event as part of the Troubles that triggered things off, but I've tried to forget about it since then. I didn't want to burden my life unduly. Interestingly enough, if we're focusing on North America, 1970, 1971, when we can see this sort of spike in activity, which I think is curious compared to the rest of the period of time that we're talking about. This is the time when Puerto Rican separatists were very active in the US, which I didn't know. Now, before I get ahead of myself and say, oh, there's no dense change points here at all, there's something going on in 1998, very clearly. January 1998, we can see a change in North America, Middle East, and Western Europe. That's curious. I said to myself when I first saw this, have I discovered that Francis Fukuyama was right after all? Was there indeed the end of history in the 1990s? Did we become more mature as a species? I must go and look at some of the other variants. Sure enough, here we get 1998. There we go. Everything seems to be changing in 1998. Well, this doesn't seem to be a coincidence anymore. There's a slight spoiler consensus coming here, but I will comment onto that in a moment. But before I move on, just wanted to say that very clearly this can deal with sort of variants on a vastly different scale. So we were talking before about Middle East and North Africa. We were unfortunately there had incidents, 100 plus per month in the region in the 2010s and so forth. And if you're living in Australasia and Oceania, by contrast, it's quite an unusual month if you've had, even more than 2 events over the last 50 years. So, pro tip: if you are a person in 1970 and want to stand the greatest chance of avoiding terrorism, move to that part of the world. Now then, I feel like I should address 1998 because I've teased it enough. It is not, in fact, a time in which suddenly the probability of a terrorist attack seemed to drop all over the world for reasons of maturity and so forth. It's when they changed the definition of a terrorist attack in the database. So I lied to you before. I said that they had these 3 slightly strange different definitions for what constituted a terrorist attack. They changed that definition in 1998. And as a result, it was harder to make the grade to be a terrorist incident in 1998. Now, at first I was disappointed and I thought, oh, I've not found something cool. Then I thought, hang on, that's actually quite a nice validation of the method. We've found something that should be there. We found a dense change point that should be there. And it also seems to suggest that there aren't any real, quote unquote, dense change points. That is to say, the causes of terrorism and the impacts that they have remain fairly localized. And that seems to be in contrast to what the news say, but agrees with the sociologists. And it's at this point that I have this horrified realization that I'm agreeing with the sociologists. I'm not entirely sure how I feel about it. So here are some conclusions. I've talked about 1998 already. Should mention as well that there are also interesting things going on with respect to records in the early 90s for reasons of communism collapsing and so forth in parts of the Soviet sphere. Made the records were more readily available in those parts of the world. So you might have seen that I think Central Asia was on the previous slide, sort of went from nothing to suddenly being something as a result of reports reaching the start consortium. Okay, I've got 15 minutes left. I could talk a bit about some of the problems with this and Omen, which is the online version of this method, which kind of attempts to do what we've talked about so far, but is also non-parametric and works with streaming data. But it depends whether people want to do questions for 10 minutes. I don't know how long we want to go on for. I can whiz through this last bit. What would people's preference be?
Oh, yeah. I think you should carry on for another 5 minutes if that's possible. And then,
5 minutes, great.
Spend time for questions.
Super. In which case, what I will do is I will get to a certain animation and then cut straight to the results and cut out the pointless theory therein. It's pointless and it's also unpublished theory, so it's stuff I'm slightly less confident on than what I've talked about. So I've talked about the fact that for this subset we have this negative binomial setting. This is a generating model. I'm making assumptions about the data that some would argue are too prohibitive, and I think probably have a very strong argument for saying are too prohibitive. Next, so in everything I talked about up to showing you the picture, I was just talking about a single change point, detecting a single change point. And suddenly in the analysis, we have multiple change points. And the reason that happened was because under the hood of this subset test statistic, I'm using a method called wild binary segmentation, which comes from Piotr Fritzovitz from about 10 years ago now. It's a very, very good, cool method, but it's very, very non-sequential. I need to have seen all the data before I even start to try and detect anything. So these are both problems that have been relaxed with this method called Omen. And this is probably the worst acronym of the entire talk. I'm going to look away. Yeah, it's not great. Yeah, it needs work. If ever this is going to properly through the light of day, it needs work. But there we go. That is what Omen stands for. And it's a new method designed to meet all the requirements of being online, multivariate, and non-parametric. This is still relatively unusual for the change point literature. When I set out trying to do this back in a few years ago now, there was nothing in the literature that existed as far as I knew that did all these 3 things at once. There are now a couple of efforts, but this I think has certain pluses and minuses compared to those aforementioned efforts, which I'm happy to go into later on. And the method is composed of 3 stages. There is a learning stage, a monitoring stage, and a verifying stage, which I will illustrate through a synthetic example. So here we have a 3-variate system, huge number of variates, as you can tell, no expense spares, with a change point at time 70. And I think in the top one we have, again, negative binomial data, count data again with a slightly higher over dispersion after time 70. In the middle plot, we can see a Gaussian change in mean and variance after time equals 70. And at the bottom, we have exponential data with change in rate after time 70. So at this point, I shall illustrate the change point, and I shall attempt with all the alacrity of everything you've seen so far, which is to say no alacrity whatsoever, to share an animation illustrating all of this. So I don't know whether people outside the room will be able to see this. It's not yet on the screen, so I will get it on. But I spent too much of time attempting to do this to forego it now. There we go. Hopefully everybody can see this animation, and hopefully eventually we'll agree it's worth it to share it somewhat. Okay, so we're halfway through. Just to recap what these three phases are. So a learning phase, we've got a monitoring phase, and we've got a verifying phase. Stage 0, 1, and 2, if you like. And the idea of this is to try and kind of be conservative in terms of where we're declaring changes or not, but also to be as accurate as we can in terms of detecting the change points themselves. So before, with the theory that we had, we were talking about having as few false alarms as possible, being as absolutely sure with these change points as we can. And we also want to have good power in detecting the real changes. So here we have the learning phase, which is this red window there. To use that as kind of a benchmark for the future data. And then we're going to use in our monitoring phase, which is this blue window, a comparison between that data and current data to see if something started to go wrong. And in the verifying stage, which is in silver there, we could see, yeah, something had gone wrong. The orange line comes up, which we'll see again in a moment as things go on. So orange line is going to come up in a moment because sometimes false alarms get flagged up. And the verifying stage, stage 2, gets called in to sweep for a change point, to do a triple check for a change point. So let's recap that one more time, because even with a fairly slow animation, it was still too fast for me. So it's doing some learning here, learns what's going on in this window, not going to declare any change points here at all. Then it's going to do some background monitoring, and then suddenly it flags something up in one of these variables, and it sends in the verifying stage, stage 2, to confirm whether there's a change point or not, detects a change point, and starts again. So it starts the learning all over again. And here it is a dense change point, but there's nothing to say it couldn't be a sparse change point. And it's going to detect both sparse and dense change points again in the same fashion as subset. So we've got 10 minutes to go. What I'm going to do is I'm going to cut straight to the chase and just indicate what we found with respect to the global terrorism data, because I did eventually get that. So yeah, we do some learning. Learning is based on the empirical cumulative distribution function compared to learning window. Don't really need to canvas this in too much detail right now. We do some monitoring, have a test statistic, and we have some theory, which says that not only do we not have many false alarms, at least according to the theory, but we also have good power to detect real changes. And we have this stage 2, which is this verification stage. Don't really rise too much at this ridiculous 12 plus multiplied by 5 times 5 plus root 2 over 23 number. I've already rolled them enough that I'm, still staring at the back of my skull, and we've got some horrible looking numbers there. Okay, so we applied Omen to the global terrorism database, and I will go back to full screen, which is Control L, Control F,
Control L, I think.
Control L. Oh, I thought it was Control L. There we go. Thank you. Very kind. Cool. We applied Omen to the GTD with some changes from the subset analysis. So I went straight in at the deep end, and I said, last time we were just looking at regions. I want to look at countries. And not only do I want to look at countries, I want to look at countries on a day-by-day basis rather than a month-by-month basis. So things now are very, very sparse. And I think that assumption has sunk things slightly, but still with some things that I want to say. So I will get to that in a moment. Beyond that, no data generating assumptions were required. I just gave it the data set and asked it to go. So there was no negative binomial nonsense. There was no kind of, assume the over dispersion doesn't change unless the whatever. Talked a bit about regional versus national. So moved on to national now on a daily basis. Some countries were a bit awkward, unfortunately. If you're interested in a specific country that kind of massively changed politically between 1970 and 2017, come and speak to me. I'll try and see if I can remember what I did, because what I did varied between country. But the USSR in particular was a pain because of the whole 1991 thing. And this kind of learning window, which I would have talked about if I'd actually wanted to plan out the time for this talk properly, is essentially how long, you know, how much time are we in stage 0? How many things are we? How many time points are we learning for? Okay, so I'll just choose 3 countries because you know, I like the number 3 when it comes to data visualization. Bangladesh, Colombia, and Nicaragua. So we talked about Colombia right back at the start with this drug economy stuff. And yes, we can see, again, mid-1998, or perhaps early 1998, for the reasons we talked about, does indeed sort of eyeballing it have a change point in it. Now, when we do some change point detection, it's quite clear that we do find some false alarms. Some of these could be dense changes. So, for example, if we look, I hope people can see this hand. There are 2 changes that are very close together between sort of maybe 2007, 2008, and this one here. So the dense changes going on here when I do things on a country by country basis. I'm pretty sure these are to do with the global financial crisis, which is interesting because I didn't see these on a regional basis. But when it came to national bases, they did keep cropping up when I varied the learning window from sort of 60 to other values. Otherwise, though, there are clearly some false alarms, and there's no getting around it, unfortunately, which I think is just a product of the fact that, yes, much of these data are quite sparse. But at the same time, there are some curious phenomena that we do pick up on. So, for example, in Bangladesh, you see in the first half of 2015, this sudden spike in terror activity that we detect. And I didn't know about this a priori, but just going straight to the bottom bullet point here, the political crisis in early Bangladesh, in early 2015, you detected. Didn't know this was a thing. 6 months where the country was essentially in somewhat of an uproar. And I've talked about the financial crisis already. And this time we do actually detect the change at the end of 1992, which curiously we didn't when we did things on a regional basis, which I'm not too sure what to make of that, but nevertheless, it's a thing. Okay, so I've introduced Omen. It's online, multivariate, non-parametric, and hopefully with a few minutes to spare for questions at least. Built on subset. So had I had time to go through it, which again, planning but on my part. Essentially, part of what's going on is it's using subset as a test statistic underneath. It appears to have good theoretical and empirical properties, but some work remains when it comes to specifically this data set and identifying the nature of changes for a general stream. Great. And there's also some stationarity issues that I want to, or would have focused on were I staying in academia, but alas, I'm not. And this is indeed the final day, but I am an academician. So thank you very much for rounding off this part of my career nicely. And if you have any questions, be delighted to take them. Thank you.
Very much, Sam. We have time for a couple of questions, either online or in person.
Why don't we start with questions in the room? Not me.
Shall I go first? So for this particular application, is it, from a sociologist's point of view, we don't really care about change points, we care about periods.
Right, so where you may be...
we care about pairs of change points.
I see, so where you're going from
behavior
A to behavior B to behavior C. Yeah,
so
back to behavior A.
So does that affect your, in the method where you're thinking about false change points?
Yeah.
Because really, I mean, take the Bangladesh, for example, it's a period of political instability. So you want one change point when it starts and one when it ends.
Precisely.
So you've got an independence assumption between your false discovery, which for this usage in particular is probably not valid.
So that's a very good
I would
point.
argue.
No, it's an extremely good point. So there is a method called SMV kappa, which was created by a friend of mine. Who's also now in industry, funny enough. But essentially what that does is it, in real time, in the multivariate sense, will detect both change points, I think, maybe not change points, but it certainly will detect what we might call collective anomalies, which is describes precisely what you're talking about. That's to say, going from regime A to regime B back to regime A. What it can't do is regime A to B to C. So it's sort of, you know, having that independent assumption there would be an issue. But yes, you're quite right. So this method has strictly less power than that method in that example. But that is, again, fully supported by a package, which I'm happy to point you to if you're interested. I'm not sure if it's non-parametric though, but I will look into it.
Are there further questions?
So thank you for the talk.
Thank you.
Can I ask if there's any way to encourage change points not to be too close one to another?
So a minimum segment length is the typical parameter. And you'll notice that I use the Weasley phrase of learning window of length 60. And essentially, when I said that it's totally non-parametric, this method, I lied. I'm sorry, I can't resist myself. So the learning window is basically saying for the 60 time points, I'm expecting no change point. I want stationary behavior in order to actually learn about kind of what the status quo looks like. And that's effectively a minimum segment length by stealth. So I'm saying that if we actually want to use this in real life for this specific example with this window length 60, we need to have no change points that are closer than 60 times. I could relax this a little bit if I knew a bit more about the data. So for example, if I knew it was Gaussian or I knew it was sub-Gaussian, say, I would probably feel more comfortable lowering this. And if I had not as many variates, I'd probably feel comfortable lowering this. But yes, this is kind of a minimum segment length. And in a lot of the methods I talked about, there are implicit assumptions on minimum segment length. So for example, just to take the kind of most extreme example I can think of, if you're dealing with a situation where you have k parameters that could possibly change, that means you have a minimum segment length usually of k plus 1 for various theoretical reasons. But that's kind of the best you can do. And for PELT, something like PELT, I think in the package normally it supports a minimum segment length of 10. But in theory, it can be as low as 2 if you're dealing with a sort of single parameter changing like a change in mean. And then there are things like the wild boundary segmentation where, good luck with segment lengths and so forth. But yes, I think this is probably the most extreme. This window length of 60. Again, you can lower it if you're in situations where you know the data are a bit better behaved than I don't know anything about the data. But yeah, to be borne in mind, and that's a really good question. Thank you. Sorry for watering on.
Sure. I missed what sort of error, type 1 error, you're trying to control.
Sorry, yes. So type 1 error here is specifically in reference to the hypothesis, if you like, the null hypothesis of no change versus the alternative hypothesis of there being a change. The type 1 error here is just there is no change, but I've erroneously detected a change. So I really should just refer to this as false alarm, shouldn't I, rather than type 1? That would have been better. Now I think this is all the things I learned about how I should give the talk when I'm giving the talk. Yes, I might false alarm.
Sorry, following on that, and do you need to control that each time point every time you make a decision on the whole data set with all the possible?
So the way that this is typically controlled is by setting the parameters in a certain way before you start. So you can either do this from theory, so these alpha, beta, k, or you can do it by doing simulations from some well-behaved null situation. So the alpha, beta, k that I showed you halfway through the slides, that works nicely for Gaussian change in mean, works well for sub-Gaussian settings. But for the specific GTD example, I think we created these through simulation. I think at least one of those parameters was born from simulations rather than specifically from theory. So yes, that wasn't. I could have been more kosher there. But never mind. I hope that answers your question.
Well, I mean, it was just because probably the type 1 error, everything depends on the number of change points. You are increasingly getting more or less.
Exactly. Yeah. No, it's a constant chicken and egg problem when it comes to being a change point detector. Yes, the more one attempts to control it, the less power we tend to have, which is a frustrating aspect of reality. Yes, hopefully, certainly seem to have reached a nice compromise with subset, getting there with Omen, but some teething problems.
Is there a question in the chat? No. Okay. Any final questions?
I had one maybe. Thank you so much for the talk.
Thank you.
How you have some kind of intuition for how well these methods or your Omen method in particular performs in kind of context where there's periodicity involved? Because it kind of goes one of two ways. Either, let's say there's some kind of 5-year cycle like El Nino, that kind of thing. Do you want to get a change point every 5 years and kind of once you've had one and you've seen that there's a trend, kind of more confident in allowing a future one, or really because it's actually just the same system on a periodic cycle, do you actually want no change points? I guess it depends on.
Yeah, that's a fantastic question. So in the latter setting where we're just looking for changes from normal behavior, where the normal behavior can be that periodicity. Omen actually works surprisingly well, which is bizarre because it's all based on kind of order statistics theory as I blast through those final slides at the speed of light. And yeah, it's essentially if something varies just a little bit from that, for reasons that theory doesn't yet explain, we're just able to see it quite well. But all bets are off when we tend to use other theory or other methods. And certainly for that first paradigm, I'm not entirely sure if Omen would be any good for that as well. So what people have tended to do here for investing sort of differently scaled change points, if you like. So I saw a rather excellent paper on pyramid recurrent neural networks, sort of dealing with things from a frequency-based setting. And their application was the analysis of bee waggle dances, which, yes, I don't know whether I'd rather look at that or terrorism, quite frankly. The literature's a bit sparser, is what I'm saying. But it's no less important a problem.
Great. Well, let's say thanks to Sam again for a great talk.